Swayam Prabha. Digital India. Educated India.
Okay, welcome back. So, today we will start with alternator windings. That is the first topic that I am going to take. My idea is basically to explain to you construction of the stator and rotor in an generator, a synchronous machine, also called as an alternator because it produces rotating MMF or rotating because it creates alternating currents and alternating voltages. So, it is also called an alternator, and that knowledge subsequently the details of the construction of the winding and so on, that knowledge we will take forward later on when we do induction machines. So, our sequence is, if we sort of take a brief pause and recap, we have initially also right at the beginning of the course when we discussed some of the things like why AC systems, what are its advantages, why does the society depend upon electricity as a for its requirements of energy consumption, whether it is light energy, thermal energy, mechanical work, or whichever way you think of it. And now even you have EVs, electrical vehicles coming into play. So, all the while if you see there is a growing dependence on electricity. So, your mobiles work on electricity, your watches now work on electricity, and anything, even a thermometer works on electricity. So, I am just taking a pause and again coming back to the fact that the importance of this course is because the complete human civilization is depending upon the electricity, and unless we understand this electricity well, how it is generated, how it is transmitted, how mechanical or heating or light energy is produced. These are the three main consumptions, right? I mean, you have lights in the night, in the daytime, you have mechanical work done, you see all the trains work on electricity. Nowadays electric vehicles are working on the road also, the cars and the scooters and the bikes are working on electricity. Your refrigeration, both heating and the converse of it, refrigeration, the refrigerators in your house, the air conditioners, they are working on electricity. So, whether it is heating or cooling, whether it is transportation, whether it is light, whether it is any other thing like MRI device or some scanning which is done in a hospital, or anything, lifts in a building, escalators in a mall, whatever it is, if you look at it, you cannot practically imagine a life without electricity, generation, transportation and utilization. So, these are the three things. Generation is generators, transportation is the grid, and utilization is all the devices, the gadgets, the computers and everything that you see around which is using electricity. And in this first course, basically we are getting some feel about this, how it is generated, how it is transported. So, generation is using alternator. So, I started initially this course discussing that, and again I am now coming back and going to do a bit more deeping into into the generator in this lecture or two, and then a few lectures, maybe, I don't know how much it is going to go, whether I can do it in one lecture, two lectures or three lectures, let us see. And then generation. Transformer is a major piece, transformer is a major piece in efficient transportation of this electricity, because you do step up and step down using transformer. The generators typically may generate up to 30 kV at the most, but your transmission voltages are 400 kV 3 phase, 765 kV 3 phase. Larger the distance to be covered, higher should be the voltage level, because then for the same power lesser is the current required, and therefore lesser will be the I square R loss, and lesser will be the voltage regulation or drop in the wire. Now, I think some of these statements I have made earlier in the beginning of the course also, and I am repeating these statements again now midway through, or maybe 2/3 or whatever, 67-70% course is done. But I think now you can appreciate the meaning of this. It is not like it should not be now like it coming from me, but like it should be like coming from you within oh, I know this. And so the transformers are required to transmit this voltages step up and step down, so that electricity is transported very efficiently, not just efficiently, but very efficiently across the grid, which consists of transmission system, which is typically meshed, and distribution system, which is typically radial. And transmission systems higher use transfer hundreds of megawatts. One 3 phase wire may be carrying like 600-700 megawatts, 220 kV, and so the voltage level therefore also is, when the megawatts go up and current has to be retained to a lower value, then what has to go up? It is the voltage level which has to go up, because the V into I has gone up significantly, or Vi cos phi has gone up significantly, and if I has to be kept in check, because the losses are I square R and the voltage drop is Iz. So, both of this, the voltage regulation and the losses, if they have to be kept in check, then the V has to be increased. Like if you are trying to transport 2200 megawatts or something like that, you will go for a 765 kV line, because again the currents you do not want to grow them significantly. So, your transformers from the generator down to that level become bigger and bigger. But transformer is a simple device, therefore, you do not really worry. If you have seen substations and you should keep your eye open now that you are learning this course, to see you should, now that you are learning this course, you should keep your eye open. You should keep your eye open to see the substations around you which are there. You will see basically small distribution transformers around the roads, that is what you will see. If you live in apartments which are multi-storied and so on, then you would see some transformers lying there to do the step down on the distribution voltage. And across, when you are doing cross country, when you are going across from one city to another, sometimes you may come across very big switch yards with very complicated, apparently complicated looking substations. These are the transmission level substations that you would see, and you can explore them further. So, this is where your 220 kV switch yard, as it would be called, or 400 kV switch yard or substation, it may be called. Substation they call it because the main station is the generating station. So, therefore, the word used here is substation, and you will come across these substations, and then of course, the grid is meshed at the transmission level that you cannot see. That is something you only see when you draw the complete diagram of the grid. Just like the roads in a city are interconnected, just by traveling on one road you won't know. It is only when you see the map or actually do a circle or a circuit that you know that it is interconnected. Similarly, here you will have to know the map of the system to know that a transmission system is interconnected and a distribution system is radial. Distribution systems are also working at 33 kV, 11 kV, much lower 22 kV, much more lower voltages, because they are handling that bulk power which is coming from the transmission system is stepped down, and then maybe like IIT Bombay is like probably having its own distribution system. Its load maybe say around 10 megawatts or something like that, but the transmission levels would be carrying, as I said, 600 megawatt, 2200 megawatt. So, you do not need that voltage level when you are dealing with distributing electricity in some 400 acres, 10 megawatts. Then you can work with 22 kV three phase system, and that is why the distribution systems work at a lower voltage level. And then finally, when it comes to your residences, there is somewhere a transformer nearby which would have finally brought down that 22 kV also to 400 volts three phase level, and then you get it in your home supply. So, it is like crossing a ghat section or a hill. You step up the potential, again climb down and step down the again climb up, and then again step down the potential. Now, today I want to again go back to this important device called the alternator. So, the transformers we have done in detail, and now we are going to go back to alternator a bit more in detail. We had done alternator in the beginning, how a single phase generator works, what is the motivation of a three phase system. If you recall, I had said that three phase systems, especially when you are dealing with balanced system, then the three phased system will have a constant instantaneous power, while the instantaneous power in the single phase system is fluctuating. In the three phase, it is smoothened out, and you get a constant three phase power, instantaneous power. And if the speed of a device is constant, then it means that you can also get a constant torque system. So, the ripples, the oscillations, etc., those problems sort of go away. And this is possible with a nice symmetrical 120 degree separation in a three phase system. If you had a two phase system also, you could have done it, but then the two should be at 90 degree with each other. So, then the utilization of the geometry of the stator or the rotor would not be that very nice. So, therefore, we have mostly three phase systems. After that, you could have four phase, five phase, multi-phase systems, but things have standardized to three phase system. So, now with this small recap of the course and the different devices that we have seen, transmission lines usually is taught in a course typically in IIT Bombay in the third year in the electrical energy systems course, where we discuss transmission lines and their performance in far more detail. Some of these transformers issues are also we come back and discuss these transformers also there. Mostly we discuss phase shifting transformers, voltage regulating transformers, some of those things also we discuss. Current transformers and voltage transformers I had talked a bit. Usually that is discussed in much more detail in a protection course, because after stepping down to like 1000 ampere to 5 ampere, and then we use it for sensing whether there are any faults in the system, there are any trouble points in the system, or the voltages may be 400 kV may be stepped down to 110 volts three phase, and then fed to a microprocessor or a digital relay, which will again primarily try to see if there is a fault in the system, and if there is a fault in the system, then it wants to isolate that piece of equipment, So, they are instrument transformers, their purpose is only measurement, they do not have bulk power carrying capacity like a generator may be like 20,000 kVA for example. So, here this will be like very small few kVA, few volt amperes, 10 volt amperes, 100 volt amperes like that kind of a generator, not a 20 MVA generator, you know, just like I talked of just now, I mentioned one example. So, the point is those instrument transformers, their purpose there which we have not gone into, but I am just mentioning there is that we want fidelity in the reproduction of the waveform as is happening in the AC system, same should come follow here. If there is any because when there is a fault there will be transient and there would be distortions, we want those distortions also to be captured properly. So, those are built towards fidelity, while what we have discussed mainly in this course is power transformer, means power transformers. Power transformers means we want to basically transfer bulk amount of power step up or step down through these transformers. So, that is the predominant use, and so the specialized equation, those things are discussed much more in a power system protection course which comes usually in the 4th year in IIT B curriculum. So, you will whatever you learn in this course, what I am trying to sort of say, you will get opportunity to dive deep more and more as you proceed further. Now, coming back to the alternator windings, which is the topic of my discussion today. Let us first consider why alternators are usually constructed with AC winding on stator and rotating poles, that is the electromagnet or the DC winding is rotating pole, or the DC windings are on rotor. Just a minute. Okay. So, this is usually the thing. So, let us say that you have a 20 MVA, which is to say a 20,000 kVA, 11 kV, 3 phase alternator. Okay. That means 3 phase synchronous machine. So, if you write this S as for a 3 phase machine as √3 VI, then you will get that 20,000 is equal to 1.732 into the current capacity IL into 11, right, where this is the 3 phase line to line voltage and this is the line current. So, if you calculate the line current here IL, this is going to be 10550 amperes. Now, suppose you had AC winding rotating and DC winding or magnets stationary. Sometimes you see this construction in the DC machines. So, it could be like N, S and a 3 phase rotating winding somewhere here. It could be a construction like this, or or like I mentioned it earlier, you can have one winding AC winding here, then this is the A phase, then this will be the B phase. So, the B phase winding would be somewhere here, and then the C phase winding will be the axis of the. So, if this is the A phase axis, this is the B phase axis, this is the C phase axis. So, therefore, another 120 degree means C and C dash. So, 120 degree means, so this is the B phase conductor, and so this is the A phase conductor. Yeah. So I get 90 degrees here, another 30 degrees here, then the corresponding B phase conductor came here, and so this will so I will get I have to go another 120 degree here. So 60 degrees here and then 60 degrees here. So what I marked as C dash is incorrect, this will be C. So the C conductor will come here and the corresponding C dash conductor will, the opposite conductor will come here. So this is my A phase, this is my B phase, this is my C phase, and in this the rotation is usually the direction of the rotation is taken to be anti, the normal convention direction of positive direction of rotation is anti clockwise. So you would get something like this, and the north and the south poles sort of sitting here. So then what would happen? I am sorry, I made a mistake. So I made a mistake. This would be B, this would be B dash. That the what I drew earlier was when the stator was means the AC windings was on the stator and the rotating windings was on the rotor. That is how I had done it in the initial part of the course, and that is how it is actually in practice, but I am now explaining to you why it is so. Means one is knowing what it is, another is trying to know why it is, and the third thing is the construction, how it is. So now here what we have done is, see this A is cutting, this is the direction of this would be the south pole. So the flux lines are like this A phase is cutting this here, 120 degrees, that is T by 3 time later, the B phase conductor should face exactly the same geometry in motion. So therefore this should be the corresponding B phase conductor, and 2 T by 3, where T is the time constant of one revolution, the same picture should be seen by the C phase corresponding conductor. So therefore I mark this as C and this as its opposite conductor C dash. So voltmeter or whatever is connecting, measuring voltage across this. So this is, in this case, see usually what, if I write this as A phase winding, if I show this as B phase winding, and if I show as this C phase winding. So each winding has two term end points. One side we will join them. Usually the alternator windings are connected in star. So you will join it here, and these three windings have to be taken out, A, B, C. And how do you take it out? So they come on a this, if this is the rotating part, and I get this A phase winding out, the other one is joined here, then there will be some kind of a brush arrangement, and so there would be this what is known as the slip ring arrangement and a brush, carbon brush or something sitting on it, so that this conductor is free to rotate, yet the brush which is so this is rotating like this, a brush is sitting at the top of it like this, the brush taps that current out and moves it further. So, this is not a north pole, this is a brush which connects to a wire which is outlet to outside world. So, therefore, how many slip rings and brush gear, all this brush comes with a proper gearbox arrangement and so on. So, how many slip rings and brush gear is required? If the AC winding was on the rotor, then a total of 4 brush gears and slip ring windings will be required if AC winding is on rotor. 3 for here, and this one is also not usually kept just tied and left, right, like we have to ground it, and usually it is grounded through some resistance to limit fault current, and also to see that this voltage is enduring unbalance does not change from neutral value. So, it should also be kept very close to 0. So, therefore, you have to ground it. Then again there is a rotating part, and that rotating part has to connect with something which is static. So, in between you need this slip ring and again a brush gear arrangement. So, a total of 4 of them would be required. Now, each of them should carry how much current? Rated current, and the rated current here would be, if I have a 20,000 kVA, 20 MVA, 20,000 kVA, root 3 into line to line voltage, let us say is 11 kV into this current I. So, this is also kVA, this is also kV. So, the current will turn out to be in amperes, and the IL will turn out to be in this case approximately 1050 amperes. So, the current, the thickness of the wires, the conductor, everything should be designed for to carry this large current, and insulation levels for brush gear etc., everything should correspond to 11 by root 3, which is around 6.35 kilovolts, because the rest of the world is including the external box and everything in which the alternator is housed is going to be at the ground potential. These windings are going to be windings, and the gearbox and everything are going to be with respect to ground at a 6.35 kilovolt level. So, much more significant amount of insulation requirement is also there. Conversely, which is what is more common, suppose conversely which is more common, suppose that this is your north south, that means the rotor is, magnet is now rotating, and the stator so if I put the A phase winding A dash here, then this is my axis of the A phase winding corresponding, and this one is rotating in the direction of rotation is like this. So, the B phase conductor should see what the moving geometry that the A phase conductor is facing now at say t equal to 0, the same should be seen by the B phase conductor at time t by 3. So, if it is rotating here 90 t by 4 it will be here, and t by 3 the north pole would be somewhere here, south pole will be somewhere here, and this is further 90 degrees from there. So, therefore, basically if you put somewhere here the B 120 degrees apart, if you put the B here and the opposite 180 degree side will be the B dash conductor, then this will create the B phase voltage to lag the A phase voltage by 120 degrees, and then this would be 60 degrees. So, add another 60 degrees here, and this would give you C and C dash coming here. So, the order has changed when the AC winding was on the rotor, and now when the AC winding is on the stator. Now, here no slip rings are required for the 3 phase AC windings. Why? Because it is on the stator, and the relative action is the same, right. The flux cutting the conductor, and in t by 2 time flux changing from phi to minus phi, again after t time reverting it by to phi, everything in terms of the relative movement is the same. But now no slip rings are required for the AC winding. Of course, this usually will be through a electromagnet. So, I could have, for example, a concentrated winding like this, or I could have a salient pole, not a very good diagram, but I could have a cylindrical magnet here, this is distributed, and this is a salient pole magnet. Here this is the dots, let us say, and this will be the crosses, the current that it has to cross, and then you rotate like this and it moves towards you. So, therefore, the flux lines follow like this, and this is the cylindrical rotor or magnet construction. Usually it is used for high speed machines, because here as you can see, you can properly house them inside this construction. So, they will not fly away. Suppose I have a 1 kg mass, and let us say this diameter is approximately 1 meter. So, the radius or is let us say around 1 meter, and you are running it at 3000 RPM. Where does the 3000 the dia is 1 meter, 3000 RPM, because we have in India 50 hertz system, in Europe also I think we have 50 hertz system, in USA, North America, Canada they have 60 hertz system, those are the standard levels. So, 50 hertz means 50 revolutions per second. So, in 1 minute 50 into 60 will give you 3000 revolutions per minute or 3000 RPM. So, now V is equal to omega r. So, omega we know because the time period is 20 millisecond. So, omega will be 2 pi by 20 milliseconds radians per second. V is going to be, the radius is to be taken as, r is to be taken as half meter, and m is, I said let us consider a 1 kg mass which is rotating, then the mv square by r, this is the centrifugal force. So, this centrifugal force will almost turn out to be around 50 kilonewtons. That is a very large centrifugal force. So, if you had this kind of a salient pole construction, rotating at 3000 rpm, this flyaway forces, that centrifugal forces, that this will make it very difficult to hold them here. But in a construction like this, which is solid and embedded in this, the forces are much more controlled. So, therefore, usually the turbo alternators, as they are called, or high speed synchronous machines, thermal generators, coal fired, usually are like that. They will be two pole machines. They will be two pole machines, and they will be rotating at this 3000 rpm, and they would have their magnets or electromagnets which are in the cylindrical rotor form. Incidentally, this has one more advantage, gives a MMF distribution, and this point I have discussed earlier, I will discuss it again sometime later, closer to sinusoidal MMF. This we have discussed earlier. If you wanted to do the same thing using this kind of a salient pole construction, then you have to taper it off. The pole tapering has to be very carefully controlled. The pole tapering has to be much more controlled, and even then you will not get that nice a thing as this kind of a distributed winding will give. So, another important term that you are picking up again, recalling it again, is distributed winding. These are some of the things, as we go to the rotating machines, we are going to discuss it more and more. So, then is it that this is not required or is not used when you are making alternators? No, not like that. Salient pole construction is usually used with low mechanical speed machines. For example, hydro generators or alternators. So, they would be like 10 pole, 16 pole, or oil fired small machines, small oil fired machines. So, what happens there is, like for example, in a hydro alternator you have reservoir at the high level, then the water flows down through the ducts or whatever, and then at the bottom of the hill it picks up enough velocity, and then it impinges on the turbine, and the turbine rotates, and the rotation of the turbine is all that how you rotate it is not important. Then you can create this action, or imagine the stator sitting on the outside here, and you can create the alternator. But if it cannot pick up that much of speed as a high speed steam impinging on the turbine blade that creates 3000 rpms, you cannot create that kind of a speed. So, suppose the speed is say 1/5 of 3000 rpm, let us say the speed is let us say only 600 rpm, then the AC voltage that you will get will be correspondingly at 50 by 1 will be 50 by 5, which is only 10 hertz. Now, can you use this generator with your rest of the system which is trying to be which is working at 50 hertz? No, you cannot use it. So, then you need to have a multiplier effect coming from the poles. So, let me for example show you a 4 pole construction. I need how many poles here? I need here 10 poles. In my example, I need 5 pole pairs, but to draw it is going to be difficult. So, I am taking north, south, north, south. So, this is one pole pair, this is another pole pair, this is the third pole pair, and this is the fourth pole pair. So, you are, if this is there and this is indicative of a stator, let us say, and here is a phase conductor. So, and this is rotating at the speed omega in the anti-clockwise direction. So, what will happen now? A, then let us call this A phase, the phase conductor is seeing N at t equal to 0. At t equal to t by 4, it will see a S, then at t by 2 it will see this north pole would have come back here. So, it will see a N, and at 3 t by 4 this would have come back here. So, it would see at 3 t by 4 it will see again S, and at t it will see N, the north pole coming back, is it not? So, therefore, therefore, if you see in the AC voltage waveform that is being generated, by this A dash turn, this A dash turn, it will have now, and we have seen it generates a AC voltage, it will generate one AC waveform in t by 2 time. This n back to n, n s n is happening in t by 2 of time, sorry, will happen in this t by 2 of time, and that one 2 pole machine construction, if you remember this 2 pole machine constructor, n rotated back s, rotated back to n, there it was happening in one time period. Here it is happening in here it is happening in half the time period. So, you will get a multiplier effect of twice, you will get a multiplier effect of twice in this one pole rotation. So, therefore, if this machine was rotating at 1500 rpm, then you would still get a 50, though with one pole pair it would have generated a 25 hertz waveform, with 2 pole pairs it generates 50 hertz waveform. So, therefore, if p is the number of poles, p by 2 is the number of pole pairs, and poles are always even, and if n is the number of revolutions per second, then f is the, so this is the mechanical speed. So, sometimes the angle which is associated with this is called as the mechanical radiance, but the electrical waveform that is generated from here, the P n by 2 is, this is the electrical frequency of the AC voltage. So, therefore, if I said like if I had 600 RPM as the rotational speed in a hydro machine, and I ask you how many poles it should have, given that I want 3000 RPM or 50 hertz, 50 hertz or 3000 RPMs on the AC side, then clearly from this formula that we just derived, P turns out to be the 10 poles or 5 pole pairs or 10 poles. So, the machines become larger. The hydro machines are much more larger machines also for the same kVA output, and because we have not seen this yet, but still I can introduce this point to you, because voltage or rather the power rating of the machine is proportional to some extent to the volume d square L. So, the proportional to the volume. So, usually the axial length would be low when d is, axial length would be low when the d is large. So, let us come to let us look at the construction a bit carefully now. We have seen some of the context has been set. Cylindrical rotor machine, it is much easy to explain. So, I will start with the cylindrical rotor machine. This is my stator. I have 2 conductors per slot. So, these are the slots, there is 2 conductors per slot, and this is the way n turns are connected. So, that means it usually goes like this, up comes like this, and these 2 conductors are in, then it will come back from here, then come to this, go up, come back here, and then that would be the end of it. So, this dot shows these are the ones which are connected. This shows these are the ones which are connected, and so on. Usually here there is no lot of space is left, because I had shown it earlier also once, if you remember, to get a sinusoidally kind of a waveform, this kind of distribution, this kind of distribution will be used. So, there is a more flattened up surface somewhere sitting here. So, there are not so many slots here, there are more slots, coming here, and this is slightly more symmetric than what I have shown here. This is that figure has not come out that well, but the flux lines are like this. This is the north and the south, and you will get again a sinusoidal or a stepped waveform which can be approximated by a sinusoid, as we have discussed it in the earlier classes. And this is your stator core, this is the rotating magnet. This is usually the construction of a 3000 RPM machine, a turbo alternator. Now, if you look at the portion of the alternator stator, the stator, whether it is whether it is a salient pole construction, that means 10 poles, 16 poles, or whether it is 2 pole construction like a turbo alternator, the stator is always non-rotating. So, the stator construction is still the same, and if you look at the stator construction, then basically you can see here that this is the wedge or gaps where this is the wedge or the gaps in which you are having this copper insulated copper wire conductors, and if it was just kept open, no, like this, if it was just kept open like this, then suddenly lot of air gap, then again iron coming up, again lot of air gap. So, the flux distribution around here, magnetic flux distribution around here would be much more haywire, and therefore, you would have lot of ripples which are happening. Hence, it is almost enclosed. So, that the flux, more air means flux will reduce, the flux lines will reduce there. So, therefore, it is semi enclosed. So, therefore, it is semi enclosed rather than fully open construction like this. And this side is the other way view of it, this side is the other way view of it, and this indicates the stator windings. This is your stator winding, this one, I am sorry, if this and this, but looking from the side view. So, this will be your this would be your stator winding, and then this is the slot insulation. So, this is your slot insulation, and this is your laminated iron core. Why do we use lamination? We have seen this earlier. We want to cut down on the eddy current losses, and laminations on the stator is no major challenge. Laminations on the rotor is a challenge because of the centrifugal forces that we have discussed, and these are the vent ducts for cooling purpose. This is how the stator winding will look to you. Now, let us look at the salient pole construction. We have seen the cylindrical rotor construction, we have seen. Salient pole construction is going to be much more elaborate. So, if you look at the salient pole construction, here is your pole face. Okay, this is your pole face. This is mainly iron, but there are thicker laminations here. These are much thicker laminations, and this whole thing, this pole face for usually tapered around here, so that you get proper reduction in the flux line, smoothly reducing along the corner. So, tapered along here, and the windings have to sit here. So, these are your W is the indication of your winding, and as I showed you somewhere, this pole is protruding from this rotating iron surface. So, this pole is protruding from this rotating iron surface. So, it needs to be bolted, and to give it strength, a mild steel strip is connected here, and this is the corresponding side view. So, if the pole is like this, there will be one bolt here and another bolt here. So, you see from here I see only one bolt, but when I see from this side, I can see two bolts which are used, and this is the riveting done to hold these laminations together. This is the bolt has to go around this mild steel thing which gives it strength, and this is the these are the wedges, and there are some copper conductors here which are short circuited. This is to help parallel operation of alternators, or to provide some kind of damping. These things are kept for this reason. So this more or less tells you now I have explained to you now cylindrical rotor, salient pore constructions, why thermal machines usually turbo alternators are 2 pole, while hydro machines, hydro alternators are usually many poles more. What is mechanical radian, what is electrical radian? Electrical radian means once you have multiplied it by a factor of p by 2 and converted it into electrical side signal, then the angles there are called as electrical radians, and the angles which are there on the mechanical side before that multiplier effect happened, this is the physical geometry, those are the mechanical radians, and electrical radians is again p by 2 times the mechanical radians, just as the electrical frequency is p by 2 times the mechanical frequency. So, I think we will take break here, and in the next class we will start with the stator windings.